Hello everyone, welcome to Ekeeda platform, and this is Ravindra here, your electrical faculty. And in this video, I'm going to talk about the equidistance pulse control. So that is actually the EPC. Second method for your firing control schemes or firing angle control. So that is the second method, which actually has replaced your IPC scheme, individual pulse control. Okay, so now we will talk about the one by one. What is the equidistance pulse control? So if I talk about the first point, it is saying that the firing pulse are generated in the steady state at equal intervals of 1 by PF using the ring counter. So we are generally using the ring counter here, which is shown in this diagram. Okay, this one. So actually these are generated, first you have to remember the key point, that is these are actually generated in the steady state and all having the equal intervals, that is of and that equal interval is equal to 1 upon PF. What is that? 1 upon PF, but that is done using the ring counter. That is done using the ring counter. So you have studied about the ring counter in your EDC. Okay, now I will move for the second point. So if I talk about the who have suggested the first, that is the Ainsworth. So Ainsworth actually has suggested this one. Okay, and using the phased locked oscillator. So he has actually used the phase locked oscillator to generate the firing pulse. So for generating the firing pulse, Ainsworth has used the phased locked oscillator. So there was actually the three main versions of the EPC schemes, that is the equidistance pulse control. So what is that? The PFC, PPC and the pulse period control. So first one is the PFC. That is the pulse frequency control. Second is the PPC, that is the pulse phase control. And third is the pulse period control. So now I will start with the PFC, that is the pulse frequency control. What is that? Pulse frequency control, and for this one. Okay, so what is that PFC, pulse frequency control? We use a voltage controller oscillator. So in the PFC, we are generally using the VCO, that is the voltage controlled oscillator, and frequency of which determined by the controlled voltage VC and related to the error in the quantity being regulated. So whatever the quantity is being regulated, so what it can be current, it can be a voltage or constant current, so or a constant extinction angle, that is the gamma. So these are the quantities actually can be regulated there by using determined by the controlled voltage VC. Okay, and related to the error in the quantity. So now if I talk about the second point of that, frequency in the steady state operation is equal to PF naught. So if we talk about the PFC schemes, so it will have the frequency of operation, that is the PF naught. And what is the F naught? We are discussing again and again, that is the nominal frequency of AC voltage, or you can say the supply frequency, you can say. So frequency in the steady state operation is actually the PF naught, and that is the F naught is nominal frequency of AC voltage. Okay guys, now we will move for the diagram. So this is a control system of the operational of EPC schemes, and here it is a summing up where the VC, that is your controlled voltage, and here it is the V1, or you can say the generating side or the primary side, the voltage controlled oscillator. Here the integration is from the for the K1 from integration Tn minus 1 to Tn. Okay, so we are taking the time before 1. Here it is a comparator which will compare with the V3. So it will compare the voltage at the V3, and then it will supply according to that the pulse generator, and then the pulse generator will be given to the output of the pulse generator will be given to the ring counter, and ring counter will send the signals. Okay, and so there are the many signals it will send, and again will be fed back to this. So this is the basic control system for the EPC or EPC, or you can say the PFC, that is a pulse frequency control. So it has the integral characteristic. and has to be used along with the feedback control system for the stabilization. That's why it has been used there. The feedback control schemes. Okay, so this is the feedback control system for the stabilization. It may be there may be a instability condition, as we have seen in the previous lecture, that due to the harmonics. So for that, the stabilization, we are generally using the control system having the feedback. It may be a positive, it may be negative, but that will depend on the system conditions. But we are generally using the feedback control system for the stabilization. Now, so if we talk about output pulse of the generator, so that is not the output, that is output pulse. So output pulse of the generator drive is actually given to the ring counter. So whatever with the output pulses of the generator, here you can see the diagram of this. So this is the pulse generator. So output of this pulse generator is actually given to the ring counter. Okay, so ring counter, it is given to the ring counter, and also reset the integrator. And we had the integrator here. This is the integrator, so it can also reset that integrator also. So what is Tn? That is Tn written. What is the Tn? That is the instant of the firing pulses is determined by. Okay, so that can be determined by this relation can be done by the integration from Tn minus 1 to Tn. K1, it is a gain, and Vc plus V1 into dt, and this is the V3, and it is ultimately going to be V3. So here it will be compared. So in this way it is written here. What is the V1? This is the bias constant voltage. What is the V3? It is the output voltage where the conversion happens, and this is actually proportional to the system period. So it is proportional to the system period, and the V1 is your bias constant voltage. Please remember this, bias constant voltage. So at the steady state condition, every time at the steady state condition, we are having some condition or initial condition we talk about, and that is the Vc is equal to 0. So at the steady state condition, the control voltage is going to be 0, and that is written here, and that we are using generally. So after putting this value, or we are getting the K1 V1 Tn minus 1 Tn minus Tn minus 1, and which is equal to V3. So we have named it equation number 1. So if we talk about the second one, Tn minus 1 equal to 1 upon Pf naught, that we have discussed in the previous one. So after comparing these two equations, we can simplify and can get the value for K1. That is, what is the value of K1? That is a Pf naught V3 upon V1. After putting this value in here, you will get the 1 upon Pf naught, and after finding or rearrangement, that is a gain K1. And this gain K1 is equal to Pf naught V3 upon V1. Okay guys, now we will move for the next one. That is the basic circuit diagram for the pulse, your PFC, okay, pulse frequency control for this one, PFC, pulse frequency control. Now if we talk about this, then the V1 is provided here, that is the bias control voltage, and it is given to this integrator, and this is from Tn minus 1 to Tn minus 1. So again it is repeating, and here the input, okay, so output of the pulse generator is given to here, and that may be used for the reset purposes. So whatever the output will be generated here, this integrator will again fed to the sample and hold circuit that you have studied in your signaling system. Then after this, it is provided to the V2 as a V2, and this as a time domain block, and ultimately you are getting the V3. So ultimately you are going to get this V3. So this circuit does not incorporate the frequency control. So this circuit, we have discussed this above one. So it is actually incorporating the frequency control. So what it does, the Ainsworth, again, according to, if I talk about the Ainsworth, then he has done that the frequency correction can be done by the deriving the V3. So if we want to do the frequency control, then we have to derive the V3, and the V3 for the V3 relation, that is the V3 is equal to V2 upon 1 plus ST1. So from this you can talk about the relation. Okay, so I can say that V3 is equal to V2 upon 1 plus ST1. And what is the V2? V2 is found from that relation, and which is equal to KV1, Tn minus 1 minus Tn minus 1. I can say that this is the PFC, and it will be done like this. So this is the basic procedure for the PFC. Now we will move for the next one.
Now, if we talk about the phase period control, this is kind of similar to the PFC. So I can say this is similar to the PFC. So what is the PFC? The pulse frequency control we have talked about in the previous slides. So it is kind of the similar thing, and the controlling you get the controlling system that we are using for this is similar to the PFC schemes only. Now, so if I talk about the second point, to accept the VC handling, it is saying that it is similar to the PFC, but what is the difference between them? That is the VC handling, how we are handling the controlled voltage. Okay, so I can say that the structure of the controller is same. VC is summed with the V3 instead of the V1. Here is nothing difference, that the V3 is summed with the V3 and not the V1, as in the earlier cases we have done. So at the instant of T1, so I can find this instant of Tn, the pulse generator. It will be integrated from the T, this will be Tn minus 1 to Tn. Okay, so we are starting from the Tn minus 1 up to integrating Tn. So here we have the gain K1 and the V1, that is the bias voltage, and dt. So after the integration of this, we will have the V3 plus Vc, and which is equal to the V3 plus Vc. And I can say that, as we know in the previous slides, we have discussed about the K1 V1 Tn minus 1, that is the V3 plus Vc. So after comparing this and finding that, we can get some values. But the thing is that the Vc is initially equal to 0, and that is actually representing the interval between the two consecutive pulses, and that two consecutive pulses is 1 upon Pf naught. So that we have discussed. And what is the Pp is the pulse number, and F naught is the nominal frequency, or you can say the system frequency. So that Vc, if you talk about the characteristic curve for the Vc, that is actually exponentially decaying, and which appears at the t equal to T1. So like this. So this is actually exponentially decaying, I can say. Exponentially decaying. Here will be the pulse numbers, and kind of this will be here, and this is kind of the starting pulses. We have generated pulses, and these are shifted like the 60 degree, like 60 degree. This is the okay, and this is the Vc exponential decaying, which appears at t equal to T1, and C was the delay angle by the decreasing the pulse frequency between the T1 and T2. So what is doing? It is decreasing the pulse frequency. So the pulse frequency will be decreased. We had the pulse generator, and we have compared with the summing up integrator and the V3. When the both values will be equal, it means that the pulse generator will be on in condition, and it will generate the pulses. Likewise, this is going to be happening. Now we can say that the frequency correction in the schemes is obtained by either updating the V1, either we can update the V1 value, that is the bias voltage, in response to the system frequency. So according to the system frequency, we can update. This is the either condition. But there may be any chance that we can include another integrator. So we can include another integrator, so that for the CC, that is the constant current, and the CA, that is constant extinction angle control. So we have the two possibilities. One for updating the VN in the response of the system frequency, another is using another integrator. So this is all about this, and we will move for the next one.
Now, the pulse phase control. What is the pulse phase control? It's generally called, that is the PPC. So whenever we say the PPC, that is the pulse phase control, and it is a kind of advanced type of other method. Okay, so now, so if I talk about the first point, it is saying that suggested by the RAM and the RANED. Okay, so these two were actually the authors related with this concept, and according to them, analog circuit is configured to this. So this is kind of the equation, or you can say the relation, which was given by the Rumpf and the RANED. Okay, now if I talk about the VCN, that is a control voltage for the nth and the control voltage for the n-1. So these are actually the control voltages at the instant Tn and the Tn-1. So if we talk about the Tn, so the time is Tn. So whenever we had the time Tn, according to that we will have the control voltage VCN. And if we are taking the time Tn-1, we will have the control voltage VCN-. So that's why we are taking the like that. Okay. Now, for proportional current, for proportional current control, okay, current control, this is I'm cutting here, written to twice. So for proportional current control, the steady state can be reached when the error or the VC is constant. So I can say whenever we have the proportional current control, okay, so that is actually saying the steady state, okay, steady state condition can be reached when the error, or you can say the VC is constant. Error, it means when there is a difference between the two voltage value, that is called the error, and which is actually compared at that end, and it will generate the pulse when both the values are equal. So there will be error 0. Or you can say the VC, that is the control voltage. So we will have the error and the control voltage that should be constant for the steady state. Now to reduce the error to 0, now if we want to the error to reduce the 0, then we can provide the pulses from the pulse generator. It is recommended to have the slow alpha control. So what we can do for reducing the error to 0, if you want to reduce the error to 0, then we can control the slow alpha control with a feedback signal, taken from the measurement delay angle. Okay, so that feedback angle taken from the measurement delay. Now this signal, whatever that signal due to that delay angle, which is derived from the frequency error. Okay, so that is actually derived from the frequency error and used to control the V1. So that V1 will be controlled from this. So this is kind of the basic points which are written for the PPSC. Then I will discuss about some of the important points, or you have to concentrate about that. The response of the PPC, the response of the PPC, that is the pulse phase control, is actually the fast and does not have the integrator. So as it is not having the integrator characteristics, okay, it is not having the integrator characteristic, so it is going to be fast because one block is reduced and there is no time for the integrator to operate. So I can say the response of that is actually the fast. Next point, the charging and discharging of the capacitor is maintained between plus minus V delta V naught. And delta V naught is changing, that is from here. This is the delta V naught, and delta V. Okay, like this, that is written. So that is related with charging and discharging of the capacitor. So this is the ramp type signal you can see there. And due to the charging of the capacitor, the step signal can be taken, because the VC at the starting, the VC were as 0 line, and due to the capacitor it is increased to some value, just like in the clamper circuit. Okay, so I can say now, so charging and discharging of the capacitor is actually maintained plus minus delta V. So above it we will take delta V plus delta V, and below we will take the minus delta V, like this. And this is your control system or controlling system for the PPC. Okay, control system for PPC. Okay, now look at this. This is the ID we had fed on the, here is the summing up the, so, and the voltage value is V1 and the VC is for the, from other end we will provide, and this is for the controlling. Now if we talk about, this is a controller and now there is a comparator. This comparator will have the V3 for the comparison, and now it will have the pulse generator. It will generate the pulse when both the values are equal, and now ultimately it will fed to the your you can say the counter, okay, a ring counter, okay, a ring counter it will fed, and again it can be reset to here. So this is the whole system is voltage controlled converter. This one assembly is called the voltage control converter. You can see there is due to these type of relation, we have the charging, okay, and this is the ramp signal. It is coming down and then going up. It is having the plus delta V and this is minus delta V, and every time we have the pulses, the pulse, the width is actually the 60 degree, and but here look at this, it is having some delay, and that delay is due to the insertion of the VC, and due to this the step will form. And here the charging is like that, but again it will repeat as the same way as it was already repeating. But this reference initially it was 0, now that reference is changed to some other position, and due to that we are having some delay here, and but again after that it will operate as 60-degree phase difference. So like that we have discussed about all these parameters related with the EPC schemes. So I hope you have understood successfully. So tata, bye bye, and thank you.